Okay. So spontaneity. Now, in everyday life, if I said, man, so and so is so spontaneous, what would that mean? What would I be saying? Like, oh my gosh, I love hanging out with them. Like, they're just so spontaneous. Maybe a little crazy, okay. Crazy is not, I wouldn't say it's the best word, but it's not completely wrong. Yeah. Unpredictable. Yeah. Like, yeah, right. Unpredictable, I think, is a good word. But yeah, maybe a little crazy usually kind of goes to the unpredictability. In chemistry, that's not really what it means. What spontaneous means in chemistry is a process that occurs without adding energy, other than the energy needed to overcome the energy barrier. Now, when they say energy barrier, that is the activation energy. That's what they mean. So if you remember our energy diagrams, if I were to complete this, we had the activation energy here that you had to meet for this reaction to happen. And technically, if you were to look back at our notes, I had shown you that whenever you're going in this uphill process, this is non-spontaneous. And then anytime you're going in the downhill process, that is spontaneous. So in chemistry speak, whenever you're at a certain process that is occurring without adding energy, you're in a downhill part of the energy diagram, that is a spontaneous process. Anytime you're going uphill, where you're having to put in energy, that is non-spontaneous. Okay? All right. So let's look at some examples. So for example, a ball on a hill rolls to the bottom. What do you think? Would that be spontaneous or non-spontaneous? Like, would that, in other words, would that happen without me putting in energy, or would it be with me putting in energy? Spontaneous, yeah. That would happen. You don't have to put in energy. If a ball, we're assuming the ball's, I guess they say on a hill, so by definition it's on top of the hill. The ball will just go down without any energy. Iron and rain rusts. That'd be spontaneous, right? Like, that just happens. Yeah. Like, unfortunately, right? Like, you don't have to go out of your way to make rust form. You just need time, But that'll happen spontaneously. Now a ball rolls up a hill, so the opposite of that. That's non-spontaneous, right? You got to put in energy to make that happen. That doesn't just happen for no reason. Heat moves from hot to cold. That'd be spontaneous, yeah. That's like we talked about when we went over enthalpy. We talked about how like I brought up like that dilemma to like, do cold things does heat flow from like the cold to hot or from the hot to cold? And we decided heat will always go from hot to cold. That's why it's spontaneous. You don't have to put in energy to make that happen. The reverse of each, if you want to make something be cold and make it hot, you have to put in energy. You got to get a Bunsen burner or something to warm up and get those particles moving faster. All right, gas expands to fill its container. Might be a little trickier. Picture it, okay? Like you have a gas and a pressurized thing of gas. If you were to the container of it, and I like unscrew the cap, would I have to put in energy to make that gas come out of the container and fill this room? That'd be spontaneous, right? That would just happen, right? It's spontaneous because things always want to. If in biology class last year you learned about diffusion and osmosis, this idea that things always go from more or a higher concentration to a lower concentration, that's why it's spontaneous. Gas would want to move from the more pressurized area that it's at. Like, think of Lysol. That's a good example. Like or Febreze or something. You don't have to like put in energy. You don't have to like have a battery to make Febreze come out of a can. You literally just like when you may think like, well, I gotta pull the trigger to make it come out, but that's just you opening the can. That's not actually you like literally putting in energy. You're just making an opening for the gas to come out of that container. Okay. Ice melts in a negative 10 degrees freezer. That one's really obscure. It's kind of weird. Focus on this negative 10 degrees. Boom, good at it. Non-spontaneous. This is below freezing. So if it's going to melt, that must mean I like got into the freezer with like a blowtorch and I'm like melting the ice. So it's kind of a very obscure example, but that would be non-spontaneous. Now, let's say I change this to positive 10 degrees Celsius. Then what would it be? It's going to be spontaneous, but why? I guess probably a better point. Why would that now be spontaneous? All right, yeah. It's hotter. And 0 degrees Celsius, that's the freezing point of water. So now we're above freezing point. So ice will just spontaneously melt for the same reason we said here, where heat's going to move from the hot to the cold. Okay. Ice melts in 100 degrees Celsius oven. It'd be spontaneous, right? That one's fairly obvious. So I think hopefully you get the idea of it. The basic idea of spontaneity, I don't think is super complicated. But yeah, on the test, I would give you maybe 1 or 2 questions that are just examples like that. And you got to tell me is that spontaneous or non-spontaneous. Now, what could make this be a little bit more complicated is when we get into like symbols for it. So the symbol we use for spontaneity is delta G. So remember that delta means final minus initial. The G specifically goes with spontaneity. And we learned about enthalpy, which was the H. And then we learned about entropy, which was your S. Whenever we were learning about exothermic, endothermic, remember I said that if you had a negative delta H, that always went with exothermic. The reason for that was if I draw an energy diagram for negative delta H would be on your y-axis, and here are your reactants, here are your products. We went down being negative, and that release in energy, this would be your delta H, which is negative here, that release in energy goes out in the environment, so exothermic would heat up the environment. Now, thinking of entropy, if you release heat, that's going to raise the temperature of things around it. So particles are moving faster. Remember, entropy is amount of disorder. Positive entropy means more disorder. So if you have a negative delta H, you have a positive entropy. And then that would also mean you're spontaneous. That would happen without an input of energy. In other words, this is all a package deal here. So you're kind of connecting together concepts here. This is where maybe it's a little more complicated, tying this into what we learned before. This reaction diagram, this would be a negative delta H, a positive delta S, and a negative delta G. In other words, this is exothermic. Energy is released as heat. Because you're releasing energy as heat, that's going to increase the disorder of the universe, increase the entropy of the universe, which is a spontaneous process, negative delta G. The sign, the positive negative can be a little confusing. How you can remember it is if you sing your ABCs, E, F, G, H, G and H are right next to each other in the alphabet. Notice how they will always have the same sign here. Technically, there can be some exceptions where they don't always have the same sign, but for our purposes, they're going to have the same sign. So if in other words, if you look at an energy diagram, it's endothermic. So let's say it looks something like this, where endothermic, you end up there, right? So now your delta H is positive. That would then mean it's non-spontaneous, positive delta G. So this would be positive delta G. And because we're storing energy in these products, that stored energy there, or another way of saying that is the environment gets colder, it's where we got the energy from that's stored in these products, you're going to have a decrease in entropy. Is there questions about this? You got to kind of cluster these terms together. Anyways, now, don't worry so much about this. There's technically an equation where some of these values can change depending on the temperature you're at. If you do like AP Chem or chemistry in college, you'll learn a little bit more about that. But this is really for your purposes what you need to focus on is just kind of memorizing these correlations here. Okay. Let's do a little bit more with spontaneity. So if I tell you it is exothermic and entropy increases, what would it be spontaneous or non-spontaneous? Or using this, negative delta S or positive delta S? Is it positive? Yeah, I agree. Positive delta S. Okay, because exothermic and positive entropy all go together. So, oh wait, I'm sorry. Negative delta G. Remember, G is going with your spontaneity. S was your entropy. That's, oh yeah, I forgot. This is always what confuses people is you would think that the S goes with spontaneity because it starts with an S. S goes with entropy. The G goes with spontaneity. Okay? There you go. Less disorder and heat is absorbed. What would that be? So break it down. Less disorder, that's talking about entropy. So if you create less disorder, is that going to give you more entropy or less entropy? The particles are more ordered. Is that more entropy or less entropy? Be less entropy. So a negative delta S. Okay. Heat is absorbed. What that means is your products end at a higher spot than your reactants. So heat is absorbed. What does that mean for your delta H? It's positive, right? You're absorbing heat in your product, so it's a positive delta H. Told you when we were going over the ABCs that H and G will always go together for our purposes. So if it's a positive delta H, that means it's a positive delta G. Okay? So, anyways, negative delta H and entropy increases. So entropy increases. Entropy is your S. Increase is telling you it's positive. Now, you don't even need to know that bit of information because I told... Yeah, what's up? Sorry, say again? Yeah, go for it. Give it to me. Negative delta G, yeah. The dead giveaway was what, like, literally what I just said, right? Because this is negative delta H, it's going to be negative delta G. Okay? One particle breaks into two, so that's a sign of entropy. So if you have one thing and it breaks apart into two, positive or negative entropy, positive, negative delta S. That's good. Good. Yeah, positive delta S. Okay? And heat is released. So releasing of heat, is that negative delta H or positive delta H? Negative delta H, okay. So then that's the key bit of information. What? Negative delta H. So it's negative delta H. That would tell us negative delta G. All right. Negative delta S and heat is absorbed. What do we think? Let's get her hand up here. Let's do some of that. No? Positive delta G, good. Again, the biggest giveaway is heat is absorbed, so it's a positive delta H. Okay? All right, number 6. A thermometer shows a temperature decreasing as two elements combine into one compound. Let's take this last part. Two elements combine into one compound. That's getting at entropy. So what would my entropy be there? Positive or negative entropy? That would be good. That'd be negative entropy because you're creating order. All right, and then if the temperature goes down in the environment, what's that a sign of for your delta H? So temperature decreases. That's because you have stored that energy from the surroundings got stored into the products, so that's why the temperature goes down. So what would that mean for my delta G if I'm an endothermic, or delta H, excuse me, if I'm an endothermic reaction? Nor, what do you think? Positive, good. So positive delta H, which would then be a positive delta G. Okay. Now this one, So here they're kind of like when we did entropy last class. What would be the what would this represent entropy wise? If you see a reaction that looks like that, what would that tell us? Huh?
Positive.
Positive.
Yeah, positive delta S.
Yeah, positive delta. How'd you know? How will we know it's a positive delta S? Yeah, go ahead.
Because you're creating more disorder because you're taking apart.
Yeah, this is, remember you count the coefficients, right? So that if you see no number there, that's a coefficient of 1. So you had a 1 for a coefficient in your reactants, and then you made 2 products, so 1 plus 1. So simplest way of saying it is like you created more disorder. So it's a positive delta S, and then we have a negative delta H, so then our delta G, it's always going to go with the delta H, so it's negative delta G. Okay, so this makes sense to you. You're in a really good spot with it, because especially for even the test, because this really, all of this really ties together a lot of the test. Other than the reaction rate stuff, this is really the big majority of the test. Okay, one more kind of thing to do with this is solving some equations with it. So they tell us for a given reaction, the S, the entropy of the products, is 100 joules per Kelvin, and the entropy of the reactants is 70 joules per Kelvin. What is the change in entropy? So what would my delta S be? Get some hands up. What do we think? No? Go ahead.
You should subtract.
Yeah. Well, which do you subtract, though? Subtracting, but like, 100 minus 70, 70 minus 100, how do you know? Yeah, delta is always final minus initial. What is, in chemistry speak, products, reactants, what's final, what's initial? Products are, yeah, so Adam, what do you think? Positive 30, yeah, so it's going to be positive 30 joules per Kelvin, because when you do delta, delta S would be the S of the products, which is your final, minus the S of your reactants, which is your initial. So S of products is 100 joules per Kelvin, minus S of the reactants, which is 70 joules per Kelvin. And so, that would equal 30. Okay? All right, now, if for a reaction your delta S is negative 40 joules per Kelvin, what does that say about our products? Greater or lesser disorder?
Less.
Huh? Yeah, less. Good. Less disorder. If there was a positive delta S, that would be more disorder. Okay. All right, so then that's really it. The rest of the, again, don't be confused about the test review. Those notes, that's like the first 3/4 of the page. So if you fill that out in your notes packet, you don't need to do it for the, I'm not going to grade that first 3/4 of the page. But the rest of the test review is just some more practice problems you would see on the test. So.